if I ever get around to editing the video of this, just for an instructional video of how to solve, how to find all the zeros of a polynomial equation, this is like where I'm going to edit and start, and cut out the other stuff. Okay, so find all zeros. Of course, I'm interested in the rational zeros. And that screenshot shows that there are some potential rational zeros. But why not just go to the graph and get a hint from the graph, because the technology is so good these days. And we have to confirm it anyway, algebraically. We have to do the math. Okay, so let's see. But we might as well use the hint that we have to save time. The rational zeros theorem, there are 14 potential rational zeros. They envision that you're going to test them all and see whether all of them are zeros, or at least until you get 3 of them. But we're not going to do that. So we put f of x in here and take a look at the graph. Two x cubed minus 9x squared plus 7x. We can always back up and use the potential rational zeros, or find the potential rational zeros using the rational zeros theorem. We can always back up and do that if we need to. Okay. Now, there's a graph, which we already saw it in the screenshot, okay, which seems to suggest that looks like there's an x-intercept at 2 and 1 at 3, but actually the third one, now we don't know it, it's just a graph, 2, 3, but there's another one over here which is not an integer. Of course, we know if it's rational, it'll be on the list, but it might be irrational, possibly. Okay. But let's use what we know and break the problem down. Now I just want an even better idea about these by going to the table. Second graph is table. What about those suspected zeros? Yeah, 2 and 3. Table says, yeah, definitely investigate. To tell whether they actually are zeros, we will do the division. Okay. Two and 3 is suggested by the technology. Okay. Well, if 2 is a 0, x minus 2 is a factor, we're going to divide by x minus 2. Of course, we're going to do it synthetically. And if the division goes evenly, that is, if we have a 0 remainder, then we will know that 2, in fact, is an actual, not potential, but an actual 0. 2 -9, 7, yeah, 7, 6, bring down the first thing, multiply and add. It's a 0. Let's run it with the 3. Technology suggests 3. Now, no reason to check it in the original polynomial, although that would work for us. Let's check it in the depressed polynomial, 2x squared minus 5x minus 3, because if it's a 0 of it, it'll be a 0 of f of x. Bring down the first thing, multiply and add, multiply and add. Okay. Now, I want to pause here and make a comment. Okay. A comment about what's going on right here. Now, we know that that represents the depressed polynomial. And at that point, you own this problem, because you always can take the depressed polynomial, set it equal to 0, solve that equation using quadratic formula, and no matter what kind of solutions you get out of that, rational, irrational, real, non-real, doesn't matter, you will be able to get them using the quadratic formula. Okay. Now, we might have chosen to do that, but we just said, hey, we got some information here. We feel pretty good about it. Let's just go with that. And in fact, once we started getting into the rhythm of using depressed polynomials, let's just continue with that to the end of the problem. Now we'll set this linear thing equal to 0 and solve it to get the last 0. Subtract 1 from both sides, 2x equals 1. Divide both sides by 2, x equals 1/2. And that's going to be our third and final rational 0. And so our answer is that the rational zeros, or the zeros, all the zeros, complex zeros, are 2, 3, and 1/2. 3 zeros of a third degree polynomial function. We got enough help from the technology that we really didn't have to mess with the rational zeros theorem.